Eric and myself, we're here to represent the dect.org project, in which a couple of other people actively participate and to which a large number of people contributed bits and pieces. So the results presented are a community effort, and we just happen to be the people that wanted to give the talk today. I'm particularly happy that we can present this at the same conference where we presented our results on GSM. GSM cell phones, of course, have a lot in common with dect cordless phones. I assume everybody's aware of what dect is, right? Cordless phones, in-house communication, but also wireless. The security of both these technologies was designed by almost the same group of people, just a few years apart. So there's a lot that these technologies share, in particular that they're completely outdated with regard to their security. I'm particularly happy that we can present both these stories at the same conference because we get completely different reactions from the manufacturers or the operators of both these technologies. Where with GSM, we're still fighting with industry over them acknowledging that there are problems. With dect, we have a much more positive story to tell, where we have engaged with industry and are actively working on improving the security, actively working on the next iteration of the standard. So this is the story to be told today and all the steps leading up to it. As a very brief overall introduction to dect, as I said, this is a cordless telephony standard meant for you to use at home, but also popular in related applications such as alarm systems, for instance, theft detection systems. It's used for machine automation. It's used for payment terminals. So it's a short-range radio that's used in a lot of areas that could potentially be security-related. It does have a pretty decent range, even though you're only supposed to use it in your house. So if there are security problems, chances are that your neighbors can listen in on your calls. dect is as a standard and specifically its security is newer than GSM, so designed by the same people, but a few years later, with the goal of making this more secure, from what we understand. But let's see if they succeeded in achieving this goal. It is, however, a very widespread technology, not quite as widespread as GSM, but there's hundreds of millions of units probably still in use and still actively pushed, even in new markets. The US just adopted dect a few years ago. So this is a very popular technology, and we hope that it will become a very secure technology too at some point. With that, let me hand over to Eric, who will walk you through all the technical details of our breaks.
Yeah, my microphone on? Can you hear me? Okay. So, what was the status of dect security about 1 year ago? 1 year ago, dect had two proprietary algorithms. The dect standard authentication algorithm, which is the algorithm which is used for pairing of two devices in dect. So if you buy a new phone like this and you carry it home, then you need to pair your phone to your base station. And for that pairing process, the DSAA algorithm is used. It's also used for potentially mutual authentication at every call. So your phone can prove that it's an authentic phone, and your base station can prove that it's an authentic base station when you establish a new phone call. And it's also used to allocate a session key for every phone call you make. So every phone call you make in dect can have a different key, a different session key, and the DSA algorithm is used to generate this key. And there's the dect standard cipher. The dect standard cipher is used for encryption of phone calls. So if you're using the dect standard cipher, then you can encrypt your phone call from your phone to your base station. So the error interface in dect can be encrypted. And besides that, the dect standard cipher is also used for passive authentication. This means that you just assume if you enable encryption for the link between your phone and your base station, and somebody who hasn't got the right encryption key won't be able to send any useful messages to the phone or the base station. Therefore, it's a kind of passive authentication mechanism. But both algorithms in dect are optional. So you can implement a dect device without any of these algorithms, and you have a valid dect device. So you can just send everything in plain and do no authentication, and it works. And there are also devices on the market which do not use authentication and which do not encrypt. In 2006, some people started looking at dect, and they were working quite independently. So there were a lot of people working on this. Well, a lot. I think perhaps 2 or 3 people already started looking at dect in 2006. And in 2007 and 2008, more people started to look at dect, and they met together at various meetings of the CCC and started to have a mailing list, and this was getting more and more people until the end of 2008, when a lot of work was already done, and we decided to publish our results at the Congress 1 year ago. And the main results this time were that the dect standard authentication algorithm was completely reversed by looking at a dect stack for a Windows kernel. So there are devices sold for Windows machines where you can use dect to communicate with a Windows PC, and you could reverse engineer the algorithm from these devices. The dect standard cipher was partially reverse engineered, so we were able to gather some information about the dect standard cipher, but we did not fully reverse engineer the cipher. There were some news out that the dect standard cipher had been completely reverse engineered at the end of 2008, but these news were wrong, and the dect standard cipher wasn't known to us completely at the end of 2008. Also, we found a lot of attacks on the dect standard authentication algorithm on the random number generators used in these devices. If you have a bad random number generator on a dect device, your security will most probably completely fail, break. And also we found some problems in dect itself and the protocol, and also in a lot of implementations. And also some people wrote an open source driver for a dect PCMCA card, which allows you to use this card as a protocol analyzer for dect, so you can sniff dect data traffic between a phone and a base station completely and write that to your hard disk and analyze it later, or if it's unencrypted, just play back the audio streams in these communications.
Yeah, back then we already had 2 very strong indications that there must be something wrong with the encryption used in dect. The one indication we find in a lot of systems is we can't review what they are doing. The standard is closed and proprietary, so some smart engineers thought they came up with a great encryption standard and don't have to share it with the public for public review. That to cryptographer is almost a guarantee that the crypto isn't as strong as it claims to be. The second indication back then, which we found through the weak random numbers, was that really no review was done on the actual implementation. While the standard, of course, called for good random numbers, none of the handsets actually implemented that, but rather used counters or something that could get away in a unit test as a randomness, but not if any reviewer what actually happened from the outside. So the lack of an open standard and the lack of reviewed implementations makes almost all dect sets, up until the ones produced this year perhaps, very weak. And those, of course, are two of the main things we try to push industry towards: more open standards and more, perhaps, certifications amongst different hardware manufacturers to adopt more best practice security and to help each other out in finding the best way of, for instance, generating random numbers.
Okay, so this was it so far at the end of 2005. What happened after that was that dect PCMCA cards were sold out very quickly during the Congress. There are still some very old cards available on eBay, however they are incompatible with newer laptops, but they work fine in older laptops. There was a lot of media coverage about these insecurities in January. One very interesting thing was that Patrick McCarty, who is a Unix kernel programmer, started to implement a dect stack for the Linux kernel. Unfortunately, he's not here at the Congress. So this is a big step for an open source implementation of dect. So far, what was available at 25C3 was just a protocol analyzer, but definitely not a complete protocol stack for dect. After the first dust has settled, the dect vendors, the BSI, a lot of security companies started engaging with us, and we talked to a lot of people about dect security. So this was all very non-public, or it was not secret, but it was non-public during 2008 and became widely known in the first months of 2009. And also the first consumer devices with improved security started to appear in January 2009, or at least at the beginning of 2009, where Windows started to fix some of the most urgent problems in dect. There are devices which can be upgraded in firmware by the user. So there was at least one manufacturer who was very quick in pushing firmware updates to their users, and they could fix some of the problems. After 25C3, the software on dect.org was also updated. There are two types of PCMCA cards. One is called the Type 2 card, which looks like this. But this card was sold out more or less immediately, and there's also an older version of this card, which is much thicker, much larger than this card. It has a double height. It's a Type 3 card. And this card is now also supported by the software on dect.org, but it doesn't fit in most modern laptop computers, only in some old laptop computers. Audio quality has been improved, and I think additional support for more codecs has been added. There were two more academic publications about dect. One of this was a diploma thesis by Alexandra Mengele. What she did, she took a lot of dect devices, I think about 30 to 50 phones, and checked how much of this dect security they implement. So she checked if these phones encrypt by default, if these phones authenticate by default, and which attacks on these phones work. So to have an overview over the current market of dect and to classify dect phones, to say this is a very insecure phone or this is a less insecure dect phone. Another publication was written mostly by Kai Ogata, who looked at an FPGA implementation for the dect standard authentication algorithm. And this has been published mid-year 2009. And also what I appreciate very much is that dect security has been added to some cryptography or IT security lessons at German universities. So in public research there was nearly nothing about dect. There were perhaps some results on the dect radio interface, how you can improve the radio interface, but there was nothing in universities about the security of the dect protocol, and now dect security is part of some IT security lessons at universities, which I really like.
It is surprising though how hacks always occur in bursts. This is a 20-year-old technology, and all the dect research has now happened within a year and a half. Everything, perhaps 2 years from the very early on. We are very glad though that this is now taken at the universities as kind of a worst-case example of how to do security, and that students are being taught what fault bits to avoid. So hopefully the lessons learned from this will much survive the burst of hacks that just occurred over the past year.
We went on to new research, so we started looking at the dect standard cipher, which was not completely known to us. Who of you in the audience knows the A51 stream cipher from GSM? Who has ever looked at the internal structure of the cipher? Okay, and who of you knows what, for example, a linear feedback shift register is? Okay, that's better. So, from a patent, we learned that the dect standard cipher is very close to the A51 cipher from GSM. So, what you see here is a picture taken from a public patent, which shows the main structure of the dect standard cipher. So, the dect standard cipher consists of 4 linear feedback shift registers. The total length of all 4 registers is 80 bits, and these registers are irregularly clocked, at least the registers 1, 2, and 3. Register 4 is regularly clocked, which means that depending on the state of the registers 1, 2, and 3 are clocked 2 or 3 times, and register 4 is always clocked 3 times. So, for example, when the dect standard cipher is in use, the registers 1 and 2 could be clocked 3 times, register 3 could be clocked 2 times, and register 4 is always clocked 3 times. So we have an irregular clocking here as in the A51 cipher. We have a clocking control unit. In the A51 cipher, you have in each 1 bit per register, where you take the bits and then clock the registers with where this bits equals to the majority of these bits. So if the special bits in registers 1 and 2 in A51 are 0, and register 3 in A51 has the bit set to 1, then only registers 1 and 2 are clocked, because 0 is the majority of 0, 0, and 1. We didn't know exactly how the clocking in the DSC looked like. We had to analyze that. And for A51, we have a very simple output combiner, which means that you just take 1 bit per register and just XOR them. And this is the output of the A51 algorithm. And on dect, you have a more sophisticated structure. You take some bits of registers 1, 2, and 3, and you put that into an S box together with the last bit of output, and this generates the next bit of output. So this is a little bit more complicated than the A51 cipher. It's so-called nonlinear output combiner, or at least you can assume that it's nonlinear. And besides that, keyloading is the same as in the A51 algorithm. So you just clock in key and IV bit per bit into the registers. So we had to get the missing parts of the dect standard cipher. What you see here is the firmware for a baseband processor, which is built into these cards. So these cards have special dedicated hardware instructions for using the dect standard cipher. they have custom logic, a custom chip, which implements the dect standard cipher, and you can control the behavior of this chip with firmware. So there are special instructions. There's special instruction in processor. This is not a standard 83. This is not a standard like a MIPS or an Intel or whatever. It's a completely dedicated instruction set just for the baseband processor of this card. And this controls the dect standard cipher. And what is written here is our standard operating procedure for the cipher. So somewhere in memory, you have 16 bytes of memory, and there you put your key for the cipher and the initialization vector of your cipher. And with this command, you enable key loading for the baseband processor here, which starts loading the key from this memory address. And then it waits 16 clocks, so it loads 1 byte of key or IV per clock cycle. So you need to wait the 16 clocks. This command here is like writing down 16 times a NOP command, no operation, just wait 1 clock cycle. And after that you disable key loading again. And after that you have to produce 40 rounds of, you have to do 40 pre-ciphering rounds, which just means that you start the cipher and the cipher runs for 40 rounds. And you just put the output away. You don't use the output. The first 40 bits of output are not used by the cipher, and these rounds are called blank rounds. So
we'll come back to the blank rounds later. This turns out to be a big vulnerability. The number 40 is pretty much random. They could have chosen any number here, and 40 turns out to be much too low for this to be secure.
Yeah, and so you enable the generation of key stream here with this command. You wait for 39 clock cycles, and then you disable the generation of key stream again. You just have to wait for 39, not 40 rounds, because during the execution of that command, 1 bit of output is produced. And then the cipher is ready for usage. So after you have you did run these commands on the baseband processor, then your cipher has been correctly initialized, and you can just start using the cipher to decrypt a dect frame or to send a dect frame over the air. And besides that, the firmware has a very useful command, which is called write state, which allows you to dump the internal state of the cipher to memory. And this command generates an 11-byte large binary large object somewhere in memory, which represents the internal state of the cipher. So this is very useful for reverse engineering the cipher, because you can just run some commands of the cipher, or you can, for example, not load 16 bytes of key, you can just load 1 byte of key, or you can skip the pre-ciphering completely, and then you can write the state of the cipher to memory and look at it from your PC.
So this level of access was extremely helpful in debugging it to the point where we could find a function that we were not supposed to know. This is a cryptographic cipher when every clock at most 5 bits are updated. So if you can look at the cipher after every bit, you see those 5 bits being updated, usually even less, and you can pretty quickly figure out what is going on there. Of course, if we hadn't had this access, we would have opened the chip, filed it down, looked at it under a microscope, which we did anyhow because it's so much fun to verify some of these results.
So here again, Starbuck helped us a lot in looking into the chips. If you don't have these commands, you have to open the card, open the chip, and look at the wiring of the chip, and have a look at all the circuits on the chip and figure out how the cipher works. But with that, you can look into the cipher when it operates, and which is very, very useful. usually you have the problem when you analyze a cipher, you just have input and output and you need to figure out what has happened in between. And with this command you can look at the cipher while it's operating. So, first thing what we needed to get the feedback polynomials for the linear feedback shift registers. This was not so difficult. We decided to load special key IV combinations in the cipher. When we started with that, we had no idea how the input of the cipher looks like. So we just knew that there are 16 bytes of memory, and this is loaded into a cipher, which is most probably somehow the key and the IV in some order. And we decided to load all possible inputs with Hamming weight 1. So we initialized the 16 bytes of memory with all bits set to 0 except 1 bit, and then loaded that into the cipher, skipped pre-ciphering completely, and then dumped the state of the cipher. And when you do that, you can write down the feedback polynomials just by hand. You just need to look at the content of the memory and you can write that down by hand. And then you can verify that using a computer algebra system to detect very obvious mistakes you might have made. The next problem was the clocking. For A51 we have a majority clocking, which means that 2 or 3 registers are clocked. And for the dect standard cipher we didn't exactly know how the clocking looks like. And what we did, we ran 1 round of pre-ciphering. You just have to run this instruction deprep twice on the baseband processor. Then you get 1 round of pre-ciphering. And then you can write the state and you can check what has changed between the states. So these 2 instructions, deprep will modify the state a little bit, and then you can check if a register in the state has been clocked 2 or 3 times, and you can try to find out which bits affect the clocking of a register. This was already presented last year, and this gave us the clocking functions. So the clocking of every register, R1, R2, and R3 is controlled by all other registers, and it's a linear function. So they just XOR some bits of the other registers, and if the result is 1, then the register is clocked 3 times. If the result is 0, the register is clocked just 2 times. The last problem was getting the output combiner. So the state of the cipher we could write had 11 bytes or 88 bits. And we knew that 80 bits are used for the content of the registers. 4 of these bits were used as a kind of help for the implementers of the cipher, or as a kind of control or debugging bits. And 4 of these bits were unknown. And we assumed that this would be the memory of the output combiner. And what we then did was we loaded pairs of random inputs, which only did differ in a single bit. And then we ran 1 round of pre-ciphering, and we then checked if these 4 unknown bits changed. So if you have, for example, bit number 23 in your state, and you load 2 random states which only differ in bit 23, and these 4 bits used for the output combiner don't change for a lot of these input pairs, then you can assume that bit 23 does not affect the output combiner. And then we could more or less get the output combiner as a kind of lookup table or S-box. And the output combiner doesn't seem to have a very simple structure, so it's more or less looks like a cryptographic S-box. Last thing what we did was we had to verify that what goes over the air is the same as what we see in the memory of the output combiner. and we used a modified version of Patrick McCarty's dect stack and a modified version of dect CLE to verify that. And this worked, well, quite great. So after this was complete, we had the structure of the dect standard cipher. We had a complete description of the dect standard cipher, and this is how the cipher looks like. We have these 4 registers. We have these feedback polynomials. The gray bits of the registers are used for the clocking control unit. So, for example, the clocking of register R1 depends on this bit, and one of these bits. I'm not so sure. I think it was 0 or 2. These linear feedback shift registers aren't coupled in any way, so each of them runs quite independently except for the clocking. And the last 2 bits of the registers are used to generate the output of R1 to R3. So the output of the cipher is a function depending on the last bit of output and of 2 bits of the registers R1, R2 and R3. And this function here looks like cryptographic S-box, so it's highly nonlinear and well, it doesn't have much structure, at least no structure we could easily spot. And it has some very useful and good properties. It's balanced, for example. So it has 64 different inputs, and 32 of these inputs result to 0, and 32 of these inputs result to 1, which is a very good property for such a cipher.
Oh, yeah, crypto stuff. I like crypto stuff. One thing I want to point out on this slide, just very high level. Here's an organization that invented A51 in cell phones and intentionally kept it limited in its capabilities so they could export it, Cold War and all that. Cold War is over, and they're asked to build a new cipher. It appears to us, of course, I don't really know the story behind it, it appears to us as if they took the A51 design and made it better in every cryptographic dimension imaginable. So they take more of the same and add things around it that all make it strictly more secure from what we understand. They released this as a cryptographic algorithm that they now think is secure, hand it over to the engineers who have to implement it, who decide to make it just a little bit faster. And you see the bold numbers here indicate which of the ciphers is stronger. And DSC is weaker only in this very last dimension here, where the engineers thought they could save a little time. This very one tweak makes the DSC cipher strictly weaker than A51. And this is just a major crypto fuck up if this was not meant to be as weak as it is. So here's I was saying earlier that there's 2 lessons to be learned from dect really, that you shouldn't keep your proprietary crypto proprietary, but rather open it to the public to review before you put it in devices. And you should make clear that you have best practice people implementing it and talking about how to best implement it. Well, this is an example of where both went wrong. The cipher was kept secret, and then the implementation of it made it all the worse. Right? So, beautiful example of how not to design cryptography. But again, this is 20 years ago, and hopefully nobody's doing this anymore, of course.
So I think many of you have ever tried to open a bag of potato chips, and when you if you're not able to open the bag, then you look for a please break here or please open here sign on the package. And as a cryptographer, when you look at the dect standard cipher, then this description of the cipher looks like a please break here sign to a cryptographer. So we started looking at the cipher, and when you look at the dect standard cipher, or you look at the A51 cipher, or you look at a similar stream cipher, then you see that all these ciphers are irregularly clocked, which means that you have some registers here which are somehow combined to an output, and the number of clocks depends on the state of the registers. So every time a bit of output is produced, this register here is clocked 2 or 3 times, and for A51 it would be clocked 0 or 1 times. This is called irregular clocking. And if you would take such a design and remove the irregular clocking, and just take the A51 cipher or take the dect standard cipher, and I make it regularly clocked, which means that every time, for every bit of output, every register is clocked exactly 1 time. Or, for example, 2 times or 3 times, it doesn't matter. If it's regularly clocked, then the cipher is incredibly weak. And if we assume for a moment that this cipher is regularly clocked, then we can easily break the cipher. The output of the cipher depends on 6 bits of the internal state of the dect standard cipher. And if the cipher would be regularly clocked, then the knowledge of one of these bits, for example this bit here, then would allow you to cut the key space down by half. So if you can determine the internal state of this bit, then you can just have to search through half of the key space when attacking the cipher, and you can repeat that. So for the dect standard cipher, if you would see 1 bit of output here, then you could then you have 64 possible values of these 6 bits here. So there are 6 bits which produce this bit of output, and these 6 bits can have 64 different values in total. So they could be all set to 0, or they could be all set to 0 except the last bit, which could be set to 1, or they could be all set to 0 except the second last bit, which could be set to 1. And there are 64 possible values of these bits, but only half of them would produce the bit of output you see here. So if you see a bit of output, then you can restrict the possible values of these 6 bits down to half. So there are only 32 possible values for these 6 bits if you see the output 1, for example. And you can just iterate over that and restrict the key space to 2 to 63 possible keys, or 2 to 62 possible keys, or 2 to 61 possible keys, because the internal state of the cipher is always just a linear combination of the initialization vector and the key. And using that you could, with perhaps 32 bits of output, break the cipher completely within minutes on a PC. However, the cipher is irregularly clocked, so you cannot run the attack on the cipher, because you don't know when the first bit of output is produced by the cipher, you don't know how often this register has been clocked, because there are 40 blank rounds, and during each blank round the register could be clocked 2 or 3 times. You know that the register has been clocked at minimum of has been clocked at least 80 times, and you know that the register has been clocked at most 120 times, but you don't know how much exactly, so you can run the attack. If you would know it, you could run the attack. And this is why we look at a linearization attack against the cipher, and we found out that you can guess the number of clocks for the first register correctly with a probability of 12%, and you can guess the clocking for all 3 registers together correctly with a probability of 0.2%, which seems to be low, but which is sufficient.
But not in a cryptographic context. Remember, we're usually talking about trillions of things, so being able to guess something with 0.2% is huge.
And if you have access to 500,000 different key streams produced with the same key, you can reveal the secret key of the cipher within 1 day on a standard PC with a fast graphics card. And if you have access to more data, for example 1 million key streams, you can recover the secret key within seconds on a PC, even on a laptop computer. The full details of the attack will be published mid-January. It has been submitted to a larger cryptographics conference, and we will get some feedback at the beginning of January. And then we will update the attack with the feedback we get from there, and then we will publish this attack. So, 500,000 key streams is a large number, and we have to look how the dect standard cipher is used in dect. And in dect you have the dect standard cipher, which generates a long key stream. And this key stream is split into 2 segments, are called key stream segment 1 and key stream segment 2. And the first segment is used to encrypt the frame which is transmitted from a base station to your telephone. And the second key stream segment is used to transmit the frame which goes from your telephone to your base station. And each frame consists of a field, which contains usually control traffic, and a B field, which contains your voice data. So, as a cryptographer, the beginning of the key stream here is very interesting for you, because these bits reveal the most information about the secret key. And if you don't have access to the beginning of the key stream and only, for example, to this part, then you can still run the attack, but the attack becomes slower, but still practical. So, we are now interested in recovering key stream. Key stream can be recovered in 2 ways. First, we can use the A field, which is at the beginning of the frame, which sometimes contains C-channel data. C-channel data is control traffic for dect. For example, if you dial a number on your phone, then this is transmitted within the Z-channel. If the display on your phone is updated because you are configuring your base station, this is transmitted inside the C-channel. If you press a key on your phone, this is transmitted inside the G-channel. And also there are phones which, for example, display the current weather or the current news from CNN.com over the C-channel from the base station to the phone, so that you can read your favorite RSS feeds from your phone. And also very helpful, there are phones which display a counter on the phone with the current duration of the call. So you can check how long you've been calling somebody on the phone, and this counter is updated once per second. And each update of the counter is triggered by the base station, so this counter doesn't run on your phone. The counter runs on the base station, and the base station updates the counter on your phone once per second with 5 C-channel messages. And usually these messages are very well structured, and it's easy to guess the plain text there. So just with the counter you can get enough data within 24 hours, which is a lot of data, but could be feasible for very long calls.
Right, but just as a little bit of baselining, of course we're not saying that the best attack on dect requires you to listen for a 24-hour long call. We're saying that this is the best attack we could come up with, but now that the algorithm is in the open, others will certainly find better attacks. We do not believe we are among the best cryptographers in the world, by no means, and this is a proprietary cipher, so it will be further and further broken. This is just the first indication that it much fails to achieve its declared security level. It will fall further.
Another way of recovering key streams is by looking at the B field, which contains the voice data, which is usually hard to guess, except if there's silence transmitted. Well, usually there is no silence in the call, but there are some real-world applications where you have silence in the call. For example, there are phones on the market which allow you to listen to podcasts through your base station. So you can use your phone's menu to select a podcast on the base station, and then you press play, and the base station downloads the podcast over the internet or streams the podcast, converts the MP3 to your phone audio codec, and more or less calls your phone, which then plays the podcast. So you can just start, for example, a Chaos Radio on the phone by pressing the right keys in the menu and pressing play, and then you will hear Chaos Radio over the speakerphone. And then you have the Chaos Radio in one direction, but most probably silence in the other direction. Also, there are applications like voicemail boxes, where the channel from the mailbox to your side is muted after it has said, please record a message, beep, or whatever. And also, there are some applications of dect where you use dect to monitor a room. For example, if you have a small child, you can just take 2 dect phones, use one phone to call another phone, and then you set one phone to speakerphone and place it in the room with your child, and go to the parents' room, mute your microphone, and switch on the TV. So you can hear what's in the other room, but your microphone is muted so that your baby doesn't need to listen to the TV.
On the lessons learned side, little higher level, these are all ideas how to guess what is being sent. Well, sending something that's completely guessable, or perhaps even has 0 entropy, as in sending silence, is a bad idea to begin with. It not only allows for cryptographic attack, of course, it also wastes battery, for instance. So this seems to be a design mistake that we can leverage in cryptographic attacks, but generally, do just not send something if you don't have anything to send. Try to add as much entropy as possible before applying the cryptography.
Another problem is sometimes you just use the control channel to configure your base station, but B field is present and it's encrypted, but it's unused. So it just contains 0 or something like this. And if you have 3 hours of radio traffic with silence or guessable data, you can also use that to recover the key. Besides these problems of dect standard cipher, you can very easily break it if you have enough data. There are some other problems. For example, the cipher key only depends on random numbers sent by the base station, so the phone doesn't add random numbers there. Also, some phones just send B fields completely with 0 at the beginning or end of a conversation. And also, if you are running a fake base station, then you can have more or less complete control over the initialization vector. So there is currently no adequate protection for replay attacks on the cipher or the protocol.
Yeah, well, there's another popular standard where this attack is possible against. But this is a common design mistake to trust the network, or in this case the base station, completely with all the security and all the random numbers, and treat the handset as completely stupid. Well, the handset does have the secret key though, and if it's stupid enough, it will tell you the secret key in one way or another, or in this case, it will tell you the key stream you need to decrypt a call from earlier. So yeah, there's a plenitude of design mistakes. Great lessons learned examples.
Okay, countermeasures. So what you can do as a user, you can restrict yourself to short calls, not to automated endless connections over dect, and you can try to avoid silence. And if you are a manufacturer, you can try to change the key in the call very frequently, because this attack needs a lot of known key stream, all generated with the same key. And you can also try to avoid guessable content in the Z channel or in the B field. Or best would be if you replace the algorithm. We will come to that. we will come back to that later.
Yeah, well, to wrap up, let me then conclude by telling you the positive outcome I promised. The dect manufacturers, being aware of this being old technologies, at first were a little suspicious of what we were doing, but finally very much embraced our insights into this technology. And over the past year, we have engaged with them to first of all discuss what we have found with them, make clear that we are not making any false assumptions and that they understand the attack thoroughly so they can patch them away where possible. But meanwhile, we have started engaging on a deeper level even on creating a new standard. Of course, the dect manufacturers create the standards, but now before the standard is being deployed anywhere, we get to look at it and we get to find design mistakes. We didn't find anything too major other than the key stream recovery attack, but it's not going to be in the standard, we hope. So, as said, there were two design mistakes here. A closed standard that nobody had publicly reviewed. That will change. The next standard, dect2, DSC2, DSAA2, they will all be published. And not only that, they'll also rely on good cryptography. We can't yet say which, but it will be what everybody probably expects it to become. The second mistake, and yeah, exactly, I forgot to skip to this page, but yeah, I hate reading slides anyhow. The second mistake I was talking about was that manufacturers screw up at the implementation level, that the standard perhaps asks for some security features that then some engineer optimizes to the point of brokenness. dect has now come together acknowledging this problem and called for all the handsets to be certified to follow best practice security. So the dect forum is creating a certification, has announced so on their webpage this week too, to give a final stamp of this is actually what we meant in the standard, rather than this barely fits the requirements, so you can chip it with our logo on it. So yeah, great outcomes, and we're very much appreciative of how welcoming the dect forum was in this, especially having made the exact opposite experience with GSM. So now what are they doing in particular to make your phone calls more secure? Of course, unless you do something to your phone, as in a firmware update, nothing will improve. But firmware updates will be provided for phones that are patchable in many cases, and newer phones of the old dect standard, that is the standard used today, will also include a number of countermeasures. For instance, changing the key more often, so that Eric can't collect 24 hours of one key stream. If you just change it every few minutes, the cryptographic attacks will have to be improved tremendously for this still to be breakable. Of course, they've also patched the random numbers and all the other problems we have pointed out last year. Now, I already went over this. Then the longer-term countermeasures will be a new standard that will require new base stations and phones, but finally give you the phone privacy you all deserve. And that is the story of dect and how it progressed over the past year. We think it's a very positive story, and not only lots of lessons learned, what to avoid, but also a great example how industry opens up and embraces security research. That's the way it should be. And with that, thank you very much. I think we have some time for questions. Question over here.
Yeah. Could you tell us a little bit more about how working with the industry went along, and possibly even name names of brands which already integrate better encryption?
Right. Well, probably the best source of that information is this press statement that the dect manufacturers have put out this past week, where they are describing it from their perspective. Really, the engagement went first just informative, us giving them heads ups on things we were going to release, but later on, really bi-weekly phone calls, working jointly on documents, all that. Go to the dect website and read their press statement. It also does mention who the members are. All the big names of manufacturers, at least the European ones, are in there. Does that answer your question?
Well, kind of. The real question is, when I go out on the other side of the street to buy a dect handset, which one I would like to buy?
Well, perhaps if you need to buy a new phone tomorrow, I would suggest try to look for a phone which is upgradable in firmware. This will be most probably much worthier to use than any phone which currently implements good security but just in the ROM. So I know there is at least one phone which can be upgraded by the user and which just costs 50 euros in a standard consumer electronics market. And this phone will most probably be a good investment for you. And if you can wait a little bit longer, wait until spring 2010, then certification of dect devices will start. And you can just have a list of phones which have been built and which have been checked by an independent test company which runs a lot of attacks against the phone and checks if the phone implements countermeasures against all these attacks. And if your phone is on the list, then it will be definitely one of the phones you should buy.
And then realistically, for the new standard to go through and be put in silicon, it will take another year.
Hi there. I noticed on your slides the lovely folk at the ETSI are involved in dect, and I believe there's a talk tomorrow about how the various individuals from security agencies like GCHQ, the British one, and I believe the German security industry have their fingers in the ETSI pie. Are you worried that those folks might try and compromise the good security going into the new dect standard?
Good question, but I think the industry groups have enough commercial incentive to make this a good standard this time, despite any perhaps governmental effort to put extra weaknesses in it. We will have to further of our possibilities, but this becoming an open standard, a lot more people will look at it and make sure that there's no bugs put in it intentionally.
Yeah.
Knock on wood.
Thank you.
Yeah, maybe one side note. I don't know how the eBay situation is on the common air PCI cards, but it's probably worth mentioning that Patrick McCarty's stack does support the PCI cards, which are a bit more beefy and maybe still available.
Okay,
Yeah,
thanks for that side note.
Yeah, this is correct. So the PCI card available on eBay is now supported by some software Patrick McCarty has written, which is not yet completely on the web. He was going to be here at the conference and tell you, but he didn't manage to do it. So, but most probably you can get an open source driver for that shortly.
One
Hello?
last question.
Okay, I've got a question about the dect and EcoDect. In Germany, the most new dect phones have the label something called EcoDect, and many seem to be compatible with dect, and some of them seems not to be compatible. How does it work?
Okay, so EcoDect is just a version of dect which tries to reduce the transmit power when the phone is very close by the base station.
Yeah.
So the idea is just don't transmit with full power. This will save your battery, and it also will make people who are afraid of radiation not go mad.
Okay.
But it has nothing to do with security.
Okay.
You can, more or less, you can check how far the base station is away or how good the signal is. And if the signal is good, you can just reduce your transmit power. GSM phones do that by default, and for dect, this is new stuff.
Okay, but you can't say it's compatible with dect or not. It's just
It's
one of the
supposed to.
feature. It's supposed to. Okay. Thank you.
Just to extend on that, is there any encryption at all, and if so, of what quality in CT and CT+?
Encryption in what?
CT1 and CT1+,
CT1.
the standard that was before
CT1.
dect.
Oh, even dect didn't have encryption at first, so I would suspect that everything predating dect won't have any encryption.
So far I know CT1 had no encryption, CT2 or CT1 Plus or CT2 also did not have encryption, but they all had very custom radio modulations. So the signal might have looked like encrypted if you looked at it with an analog receiver 20 years ago or so, but there is no encryption there as far as I know.
Cool, thanks for all the questions. We'll be around for the rest of the conference, so come to us if you have more. Well, I hope you'll have a great rest of the conference. Thank you very much.